Hello and welcome back to day 11. Today we're going to um, run into an interesting problem today. Problem that I've been sort of warning you might happen. And so today's the day. So let's go ahead and jump right into it and look at our problem. All right, day 11. Ancient civilization on Pluto is known for its ability to manipulate space-time. While historians explore their infinite corridors, you've noticed a strange set of physics-defying stones. First glance, they seem like normal stones. They're arranged in a perfectly straight line, and each stone has a number engraved on it. The strange part is that every time you blink, the stones change. Sometimes the number engraved on the stone changes. Other times, the stone might split in two, causing all the other stones to shift over a bit to make room in their perfectly straight line. It's like a Doctor Who thing. As you observe them for a while, you find that the stones have a consistent behavior. Every time you blink, the stones each simultaneously change according to the first applicable rule in the list. If the stone is numbered 0, it is replaced by a stone numbered 1. If the stone has a number that is an even number of digits, it's replaced by 2 stones. The left half of the digits are engraved on the left stone. The right half are engraved on the right. For example, the new numbers don't keep excluding zeros, so 1,000 becomes 10 and 0. None of the other rules apply. The stone is replaced by a new stone. The old stone's number multiplied by 2024 is engraved on a new stone. No matter how the stones change, their order is preserved, and they stay on their perfectly straight line. How will the stones evolve if you keep blinking at them? You'll take note of the numbers engraved on each stone in the line, your puzzle input. You have an arrangement of 5 stones engraved with the numbers 0, 1, 10, 99, 999, and you blink once. 0 becomes 1, 1 gets multiplied by 2024, 10 gets split, so it's a 1 and a 0. 99 gets split into 2 nines. 3 nines gets multiplied by 2024 for 2021976. After blinking once, those are your stones. Okay, that's enough of a description of the problem for us to get started. And here's our first set of test data, right? So we're going to want some kind of a stones class to keep track of our stones, right? So let's do our stones tests. Okay. We will call this a fact just to start. Public void first sample. I don't really know what to call this, but that's fine. We know that this is our input data, right? So var input, that's going to be our input data. What we know we need to do is we need to parse the input data, right? We know we have to blink, and then we have to see what these stones become as this arrangement. But what they're really after is a sum, or a sum of how many stones we have. So this is really the answer. How many stones do we have after we blink, right? So we took those 5 stones, we end up with 1, 2, 3, 4, 5, 6, 7. So we know that we have to check the stone count. Interestingly, this is not one of those situations where you need the actual numbers of the stones. It doesn't matter. We're not adding all the stones together. We're literally just saying, how many stones do you have every time you blink? Okay, so after blinking 25 times, starting with these 2 stones, we have 55,000 stones. And you'll see that that is my data down here. So we'll get to that in a moment. But for now, we can start with this. And we know based on this that our answer would be 1, 2, 3, 4, 5, 6, 7 stones. We will have 7 stones. All right, so what does our code look like then, right? So we'll take our stones list. We're going to want to pass the input to this. We're going to want to blink once, right? And then we can say 7 is the number of stones that exist now as a result. That's pretty much it. We clearly don't need that as a variable. That can just go right there. Okay, so that's our first sample. We're going to turn 5 stones into 7. Let's get started. Public stones, string, stone list. Right, we need that. We're going to need the ability to blink, right? So we have that. And then we're going to need We're going to just go ahead and assume long because, you know, the numbers are already pretty big. So let's see, count. And we'll throw a not implemented there, right? And then we'll go ahead and let's make sure these get skipped. Skip. Not now, not yet. We'll even go comment that one out because that's our second version, which we haven't seen yet. We'll go ahead and run those. So there's our not implementable. So that's what we're used to seeing. So what do we need to do? We obviously need to parse all these stones here, right? So let's start with putting these in an array of some kind, right? So we'll say a long array of stones. The stones is going to be equal to stone list split on spaces, and then our friend long parse. Oh yeah, and turn you into an array. So what happens then is count becomes pretty easy, right? That is literally the stone's length, long length, obviously, because we could have a lot of them. And then we blink. So what do we need to do when we blink? In essence, we're walking from stone to stone and making a choice about how to transform that stone into one or two other stones, right? So let's start with a list of long as our new stones, right? And then at the end of this, we're going to replace our stones with the new stones. Actually, you know what? It can be a list. It doesn't have to be an array. Fine with that. Because just turning it into another array seems silly. So it seems silly. Long count. Okay. Yeah, long count. Okay, so if we're going to make new stones out of this, we're going to say then for each of our stone in the existing stones, we have our rules, right? What are our rules? Let's go take a look. Our rules are zeros become ones, right? So our rules are zeros become ones, and then even number of digits gets split. Even number of digits gets split. Odd number of digits multiplied by 2024, right? Okay, so none of the other rules apply. Okay, this is really else. Okay, so fairly straightforward. If the stone is 0, right, then we're going to do new stones, add a 1. Otherwise, we're going to take our stone as text, right? And if the stone text length mod 2 is 0, that means we have an even number of digits. Then we're going to do a new stones, add a long parse of the stone of stone text 0 to stone text length divided by 2, right? So that's the first half. And then we do the second half, which is just this to the end. Those are our two stones. Otherwise, new stones, add stone times 2024 long. Okay, that is our blink. One step blink. Create a new set of stones, replace the old stones with the new set. Okay, so let's see if our test passes. Okay, looks like our test is passing. That's good. I have, this is your hint that we're going to be dealing with timing things today, right? This is obviously because I have verbose turned on. We've done it in the past, so this will be a little cleaner. Okay, now we have our first samples passing. Let's go look at our second sample, because our second sample has multiple steps. So this is going to be our initial arrangement, right? And so if we follow these steps, this is what we end up with. 125 is an odd number of digits. That gets multiplied by 2024. This is an even number of digits, so it gets split into 1 and 7. Right, so every one of these steps is an opportunity for us to void second sample. Every one of these steps is going to be an opportunity for us to count the number of stones and make sure that our algorithm is doing the right thing. So we'll take in a count of blinks, and then we'll take in the expected stone count, right? So if we look at our stone count here, we start with 2. The first step, we have 3, right? So this is going to be int blink count long expected. All right, so let's go ahead and create our stones from this, and then we'll say, what have I done wrong here? I used a semicolon instead of a comma. Okay, and then we're going to say while blink count is greater than 0, we're going to blink, right? And then remove our blink count. And then we're going to say assert equal our expected value for the stones count. Okay, so after we blink once here, we should have 3 stones. Let's make sure that passes. It does, okay. After we blink twice, we have 4 stones. We blink twice, you'll have 4 stones. Looks good. We blink 3 times, we'll have 1, 2, 3, 4, 5. We'll have 5 stones. Okay. Looking good so far. 4 blinks. 1, 2, 3, 4, 5, 6, 7, 8, 9 stones. See, that took quite a jump there, didn't it? So after 4 blinks, we'll have 9 stones. Okay, but we're still on track. That seems okay. 5 blinks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 stones. It's feeling like exponential growth, right? 3, 4, 5, 9, 13. Things are ramping up here. And the last is 22. That's what it told us. So 6 blinks will have 22 stones. After 6 blinks, whoops. After 6 blinks, we'll have 22 stones. Okay, so looks like our algorithm is doing the right thing. So basically what they're saying now is, given this initial arrangement, we end up with 55,312 stones. Okay. Well, that initial arrangement is what's sitting in data1.txt, you'll be unsurprised to discover. So what we want here is essentially this down here, right? And we don't have a result here. We have just the stones count, excuse me. So I just need to drink a little water. So what we're going to do is we're going to read the stones out of the file, right? We're going to blink 25 times. And then we're going to make sure that we got the number. So think about how fast that grew. Sorry. Think about how fast that grew. We went from 2 stones to 22 in just 6. And we're going to be at 55,000 stones after 25 blinks. That's a lot. All right, so this is just going to be for var count is 0, count is less than 25, double plus count, right? And then you blink, and then we should have the answer. And then this is file, read all text, file name, read all lines, sorry, of the file name. And we'll just take the first line. Okay, so let's run this. We expect this to pass, fingers crossed. It passes. Okay, good. So then they gave us our real data. Our real data doesn't look that intimidating. It's 1, 2, 3, 4, 5, 6, 7, 8 numbers. Okay, so not so bad. Our real data being 8 numbers means that we grow to 217,000, right? That's what I discovered when I did this the first time. Let's go ahead and uncomment this. And everything's working okay. So we have now got the right number. Oh my God. We're skipping these tests. That's amazing. Sorry, let's actually run them. Okay, we've got the right number now. Sometimes that happens, especially when you're having a coughing fit. Okay, so what's next? Part 2. Historians sure are taking a long time. To be fair, the infinite corridors are very large. How many stones would you have after blinking 75 times? Now, this is a massive number, right? This is a huge number. So it looks like we don't need a part 1 and a part 2 today. What we really need is a count number because we're not going to use the iterations. We'll call this iterations. We're not going to use data 1 again. We're going to use data 2 again, except we're going to use this as our number with 75 counts. Just so we understand what's going on here, let's take a look at that number. That is 259 trillion. All right, there's thousands, millions, billions, trillions. Okay, and then this is our iteration count. 259 trillion should be ringing some alarm bells, but let's go ahead and run these tests and see what happens. Yeah, okay. We're taking a while. Okay, we're taking a while. So what does that mean? Well, how do we figure out what we should be doing here? First of all, we're going to go ahead and turn back on verbose because I would like to see how long things are taking, right? We'll go ahead and do verbose. And interestingly, so here's data 1. So it already took us 21 milliseconds to do 25 iterations here and 26 milliseconds to do 25 iterations here, right? That's quite a while, but that didn't feel quite like a warning sign yet. But 259 trillion feels like a warning sign. So let's do this. Every time we blink, let's print a dot. Okay. Let's print a dot. And at the end, we'll, clear that out. So you can see here that we've been printing dots, and now we can get through, the first few iterations really quickly, but you can see now each one is taking incrementally longer. And that's because the size of the array is growing and growing. Because remember, we're not adding together the numbers on the stones. We're literally counting the number of stones. So you might be tempted to say, go grab a cup of coffee and come back and see what happens. But let's think about what's actually happening here and whether or not it could ever legitimately finish with the implementation that we have, right? 259 trillion stones. Well, what's our implementation? Our implementation is storing a list of stones, right? Each one of those stones is 64-bit. So each one of those is 8 bytes. 8 bytes times 259 trillion, probably more memory than you have in your PC, right? So obviously this strategy isn't going to work. So let's talk about what happens when the strategy you have doesn't work anymore. So in this scenario, what are we being asked to do? Right? We've been given some rules like order is preserved, right? Does that rule actually make sense? Order is preserved? We're just counting the stones. The actual numbers on the stones are only important when we blink. They're not important when we're done. The order that the stones were there doesn't seem to be important either. So what does that actually mean then? This is a head fake, right? Telling you that the order is preserved, but then nothing in the problem statement says you have to do anything related to the order of the stones. All you're doing is counting how many there are at the end of the day. So order is preserved is not a rule that I feel like we have to obey because I can get the answer without preserving the order. So how can I get the answer though if I need 259 trillion of these? So what else do we know about the way that this problem is designed? We know that the rules are very straightforward. We know that looking at the sample data, for example, here, we have 2 2s, right? And then down here we have 1, 2, 3, 4 2s. And we have a couple of zeros, and we have a couple of 6s. So we definitely have duplicates in our data as well. So that's an interesting thing, right? So how can we store all of the stones without storing all of the stones? Because we know we can't store all of the stones, 259 trillion of them. We would never be able to do that. What else do we know about this algorithm that we can take advantage of, right? If the stone is engraved with the number 0, it's replaced by 1. If it's an even number of digits, it gets split. If it's not a number of digits, it gets multiplied by 2024. One thing we know about that is, for example, this 2 and this 2 and this 2 and this 2 all get treated the same, right? They all fall into the category of you're going to get multiplied by 2024. Their position in the list does not matter, right? They all get treated the same. So what if we collapsed the list so that instead of storing a bunch of 2s, we just stored how many 2s we have? We treat each 2 the same so that whether we have 1 2 or a billion 2s doesn't matter, because we're just going to treat them all the same. Okay. So with that in mind, what I want to do is I want to use the fact that these tests, we're going to comment out the one that doesn't pass. These tests are now a guidepost for us to redo this algorithm, right? This version of stones is not helpful. We know that that's not going to work. I'm just going to call you stones old, right? We're going to make new stones with the same API and see whether or not we can make a new API for stones where all of that, all of these tests pass without having to change. Okay, so we know we need this to start with, right? Here's where we start again. Public long count, throw new not implemented exception. And we need to blank. So this is now the first thing we're going to think about is what is our storage mechanism? Because we can't store this as a list. But if we store the list of stones and how many of each of those stones we have seen, right? That would be an interesting way to think about this problem. And this is a common algorithm in programming. It's called memoization. So instead of storing this as a list, and what if instead we store this as a dictionary of long to long? Okay. And the key to the dictionary is the stone ID. So that's, the 0, the 1, the 2. And then the right-hand side is exactly how many of these do we have. So we're going to do this. We're going to basically say for each var stone in stone list split on spaces, select long parse, right? We want stones substone is 1, although theoretically we all would also have to be aware of whether or not any number in this initial set repeated itself. In terms of my data, it does not. So I'm not going to worry about that. But the reality is that you should be saying, hey, if I've already seen this stone, then just add 1 to its list. And we are actually going to use a function like that. So I'll just go ahead and write that function right now, and we'll start using it. So if we say add, we want to know the stone, and we would like to know how many, right? So we'll say, yeah, count's fine. So here, instead of doing this, right, what we're going to do is we're going to do add the stone 1 time. And this is a fairly straightforward thing. We're going to say if try get, if stones try get value for the stone, out var current, then stones, stop it. Stones sub stone is current plus count, else stones sub stone is the count. Okay, pretty straightforward. If we already have stones, add it to the list. If we don't, then there we go. Okay, and now count is going to be a little bit more complicated, but still fairly straightforward, right? Because what we will do here is we'll basically say stones values sum, add up how many of each we have. Notice that there's nothing in here about the key, right? We don't care what the number is on the stone. We just want to know how many stones we ended up with. And then the last thing is, how do we blink? So our initial version of blink was we could create a new set of stones. We could continue to do that. I think that's fine. So we'll unread only this dictionary and we'll say new stones. We're going to take this code. Be fairly straightforward to move this code over here now, right? But instead of a list, it is now a dictionary of long to long. And we want to add this stone to the new stones, not the old stones. So here our add function really, by the way, did not need to be public, can really be static. And we're going to take the list of stones as a parameter. That way we can work on two different sets of stones. Okay. So for each stone in stones, right, that's our existing stone. The stone is the key. So if the key is 0, then new stones, then we've got not new stones add, we've got add new stones 1. Now we need to count, and that's our value, right? So this is how we're going to shortcut all of our math. Because we're going to say, no matter how many zeros we have, we treat them all the same. So if we have 1 0 or 100 zeros, this is what we do, is we add all of them now as a 1. Okay? So next thing here, we're going to take stone key to string. We're going to do our stone length. This is not new stones add. This is, in fact, add new stones. And then once again, here at the end, we need to say how many of these are we adding, right? We're adding, again, stone value. And then down here at the bottom, this is not add, this is add new stones. And lastly, we need stone value. So once again, we're treating every stone as being the same. So we're working on all of these things as a group, and it allows us to collapse that math down. Is this going to be enough? We're going to find out. So that's a pretty straightforward implementation. Looks very much like our old implementation, except instead of using a list of longs and walking the list, we're using a dictionary of longs to counts. Still walking a list. So I guess we'll see what happens here, right? Let's run our tests and see if they still pass. Okay, they look like they all pass. But what's interesting to note here is that look at how much faster these things are. These things were taking, multiples of milliseconds before, and now we're down into, small numbers of microseconds instead. We can also stop printing dots. All right, so you can stop printing dots. All right, final test here. Is this going to work? And turns out it does, and we're able to do it in 30 milliseconds. So really, the essence of this problem was twofold, right? The essence of this problem is recognizing that we had way too much data for us to actually keep all of the data. So how can we work on this data without having it all? Another solution in situations like this, which would be really painfully slow, but still possible, for example, might be to store the things on disk. But again, 259 trillion longs on disk, that's a lot of disk space too. So in this case, that wouldn't necessarily have been the case. But sometimes when, memory is the problem, using something that you have a lot more of storage-wise than your RAM is better, right? I have, on this machine, I have 64 gigabytes of RAM, but I have a scary amount of storage because this is also happens to be my personal server. So I have like 100 terabytes of storage. So we could have tried disk, but disk would have been very slow as well. And even if I could have made it work with my 100 terabytes of storage, you might not have been able to make it work on your laptop with 1 or 2 terabytes of storage, for example. So this idea that we have to find a way to look at the data differently is a really common problem when we start looking at massive amounts of data in computer science, right? And because we tested our way into this, and we had a fairly substantial number of examples of making sure that our algorithm was correct, we were able to swap that algorithm out from underneath, ensure that we were still getting the right answers for the data that we already knew how to compute, right? And then could we get down here and now compute the data? We're basically testing our theory. Was memoizing everything and saying, let's not keep the individual numbers, but instead keep number counts. Was that going to work? We didn't know, but we were able to quickly write a version of that that we could verify was at least functional. And then when we got down here to our problem data, it turns out, yes, that's exactly what we needed to do, right? So that's what I wanted to talk about today was, remember I'd been telling you all along that brute force was someday going to fail us. Day 11 was the day where brute force was going to fail us. And you could tell not only by the number here, but when we started printing dots, which is one of my favorite things when you have loops, print a dot, and you can see that the dots were going, and then a dot, and then dot. And so you knew we had a real problem here. And the real problem for this was memory, right? The reason those were taking so long was because we were creating exponentially larger arrays each time, or lists of t is in this case, exponentially larger lists of t this time. And there was really no way that we were going to optimize this process such that 259 trillion numbers was ever going to be capable of being stored in memory. So knowing that this is a large number problem helps me describe why this is a problem. But like, I still had to sort of look at this and go, exactly what's happening. And when I saw that exponential growth, I was a little worried. And then when I printed the dots, because that's exactly what I did last night when I did this problem, when it first came out, I'm like, okay, this is never going to finish in my lifetime. This is never going to finish. So even if I had, enough space, enough RAM to store 259 trillion longs, it would have taken, until the heat death of the universe for me to compute them, at least on this, Ryzen 9 5900X. So anyway, that's it for today. Problems are starting to get a little bit more difficult. Well, this one's actually probably the first one that's really going to knock a bunch of people out in terms of not being able to finish today. Because if you've never seen, ways to cope with very large amounts of data, like this memoization that I've been talking about, you could be scratching your head. Like, I don't know what to do now. And it's okay to not know what to do. In situations like this, not knowing what to search for can be challenging. But the answers are out there. And sometimes, the difference between someone who's new at programming and someone who's been programming for, 35 years like I have, you'll find that the difference is the problems that we've seen and how well can we remember how to solve problems like this, right? There's not necessarily a judgment on someone's ability when they look at a problem like this and they go, I don't know how to solve this, because they've never seen a problem like this. I didn't know how to solve this the first time I saw a problem like this. I had to go find someone who had solved this problem, which, in the case of advent of code means going and looking at somebody's video like this to see how did this get solved? How can you do this without, crushing your computer and requiring, the ability to store 259 trillion longs. Anyway, that's it for today. Like I said, these things are getting harder. The opportunities for TDD and algorithmic evolution are probably going to be fewer and far between. So we'll see when we see you next time, but hopefully we will see you next time.